the work energy theorem, which said that the work was equal to the change in energy. Okay, so let's go ahead and work with some examples now. Here we have a cliff has 3 ledges, one 25 meters above the ground, another 50 meters above the ground, and the last is located 100 meters above the ground. If a rock of mass 5 kilograms sits on a ledge, how much gravitational potential energy does it have when it is located at the bottom ledge, the middle ledge, and the top ledge? So let's go ahead and draw a picture of this. Here I've got my rock ledge of the cliff, got my second rock ledge of the cliff, and here I've got my third rock ledge of the cliff. And as we said, this top one was 100 meters above the ground. It's the ground here. This is 50 meters. And this is 25 meters. Okay. So for our givens, we know that the mass of the rock is 5 kilograms. It's just here. We know that our acceleration is due to gravity, so that's g. And we know that our heights are the distances of 25 meters, 50 meters, 100 meters. Okay. So for our unknown, we have gravitational potential energy. And for our equation, we have that gravitational potential energy equals m times g times h. Okay. So this is really just a straight chug and plug problem. So let's solve this. So our gravitational potential energy for 25 meters is the m, which is 5 kilograms, times the g, which is, we'll just say about 10. It is 9.81, but we'll just say about 10 for now. And then our height is 25 meters. So then our gravitational potential energy at the 25 meter ledge is equal to 1,226, and that should be joules. Okay. We can do the same calculation, but instead change this here to 50 for the 50 meter ledge, and that 25 meters to 100 meters for the 100 meter ledge. So we have gravitational potential energy of the 50 meter ledge is equal to 2,452 joules. The gravitational potential energy of the 100 meter ledge is equal to 4,905 joules. Okay, so that's just a basic calculation of gravitational potential energy. Okay, so now on to our second question here. How much work would be done if we were to lift the rock up to each of the ledges? I'm sure you're thinking that work is force times distance, and solve it like we did previously, where if we're lifting up at constant velocity, Fg is equal to the applied force, or the normal force. We could do that, but there's a way to do it even easier. Remember from the last video, we have that work is equal to the change in energy, which is equal to the final energy minus the initial energy. Okay. So if we start out with a rock, the 5 kilogram rock down here at the ground, what is its initial gravitational potential energy? Well, that would be at a height of 0. So then our E initial, our potential energy initial, is 0, right? Because it's mass, so acceleration due to gravity times a height of 0. Okay, and our final energy is really just what we've calculated already. These up here. Final gravitational potential energy. So then we would have, for the 25-meter cliff, we would have 1,226. So the work of the 25-meter cliff would be 1,226 joules minus 0. The work of the 50-meter would be 2,452 minus 0. And the work of the 100 would be 4,905 minus 0. 3,4905, 2,452, 1,226, and those would all be joules. Okay. So we solved that problem using the work energy theorem. So say we were to now take the middle ledge here to be the 0 point. So instead of this being 0 down at the bottom, let's take our middle ledge to be h equals 0. How much gravitational potential energy do we then have at the top ledge? Okay. Well, once again, the gravitational potential energy is just mg times h. And we have 5 kilogram rock. With gravity is 9.81. We'll just say about 10. And then we have our h value. Well, what's our h? If the middle is h equals 0 now, to get to the top, we only have to traverse 50 meters. So then that would be our new height value, is 50 meters. Okay. And that would give us about 2,500, or if we're to use exactly 9.8 for gravity, we'd have 2,452 joules, which is exactly what we found. This completely matches this, because it's still a gravitational potential energy of 50 meters each time. Okay, so let's go into a kinetic energy problem. So a car has a mass of 1,500 kilograms and it's moving at 5 meters per second. How much kinetic energy does this car have? So our givens, always start with a guess method. Our mass equals 1,500 kilograms. It's moving at 5 meters per second. So we've got a velocity of 5 meters per second. Our unknowns, kinetic energy, in our equations are 1/2 mv squared is kinetic energy. So just plugging everything in, we have kinetic energy is equal to 1/2 1,500 kilograms times 5 squared. So plug that in your calculator, see what you get. You should get 18,750 joules. Okay. So now a little more complex problem. So the same rock from the previous page falls off the top ledge all the way to the ground. How much kinetic energy does the rock have just before it hits the ground? So we've got our top ledge here, all the way down to the ground. So this would be 100 meters. Okay, and once again, our rock is a mass 5 kilograms. Okay. So let's write our givens. Our mass is 5 kilograms. Our height is 100 meters. So it doesn't really seem like we have much to go with here. Let's keep plugging along with our unknowns. Kinetic energy in our equation, kinetic energy equals 1/2 mv squared. Okay, so we've got our m, 5 kilograms. We don't have our velocity just before it hits the ground. So this rock is going to fall just off the cliff all the way down to right before it hits the ground. Well, if we go way, way back to our kinematics, we have the two main equations. X minus x naught equals v naught t plus 1/2 at squared. And v equals v naught plus at. Okay, so our initial velocity, we know that's also a given. That's 0, right? Because it's just sitting there. It's not moving initially. Okay. So we can set these to 0. Our acceleration is only the acceleration due to gravity. Okay. So if we define this as positive y, an acceleration down is positive, and our displacement down is positive. So let's run with this one. Now x minus x naught is 100 meters, is 1/2 times g t squared. And solve for that, we've got 200 meters equals 9.81 times t squared. The time that it takes to fall all the way down if we continue solving this, let me take a second to plug in the calculator. So the time it'll take to fall down is 4.515 seconds, not meters. Okay, so we've got a time now, so we can determine the final velocity using this equation with our time. So v equals 9.81, x acceleration due to gravity times 4.51. So our final velocity is 44.24 meters per second. Okay, but are we looking for final velocity? No, we're looking for kinetic energy. So that our kinetic energy is 1/2 mass velocity squared, 1/2 times 5 kilograms times 44.24 meters per second squared. Plug that in your calculator. Should get something around 4.893 joules. Okay. So this is somewhat similar to what we calculated over here, this 4905 joules. It's a little off because of rounding and everything, but these should be the exact same. So there's a link between the gravitational potential energy at the top and the kinetic energy at the bottom. So all of the all of the potential energy at the top is being transferred into kinetic energy when it reaches the bottom. So we can look at that with these things called LOL diagrams. Got them just here. So the LOL. And you've got bar charts for your gravitational potential energy and your kinetic energy. And this O here is what's in your system. So what are you looking at the energy of? Well, we're looking at the rock, right, because it's falling. And we're looking at the Earth, too, because it's gravitational potential energy. The gravity comes from the Earth. That force due to gravity comes from the Earth. So what do we notice about these bar graphs, these bar charts? Total gravitational potential energy is equal to the amount of kinetic energy at the end. So when the rock was sitting at the very top, it had all gravitational potential energy and no kinetic energy because it wasn't moving. And then when a rock reached the very bottom at a height equals 0, it had 0 gravitational potential energy, but all kinetic energy. So all of that gravitational potential energy is being transferred to kinetic energy. So these here, you should always have the same amount of units of energy at the beginning and at the end. Okay? And that's what we call the conservation of energy, is your kinetic energy initial plus your potential energy initial equals kinetic energy final plus potential energy final. That's pretty important. So this holds true in an isolated system with no friction or work being done on or by the system. Okay, so why do we make this exclusion here? So if there's friction, then you're losing some of that energy to the heat that's happening with the road. And we define that as E thermal. And that is equal to the force of friction times the distance that you're experiencing that force of friction over. Okay, so if you're experiencing friction, you're losing some energy to a thermal energy. So you're losing the energy to friction. Okay, and if you do work on the system, you're putting energy into the system. So that would give you more at the final position than at the initial position. Okay. We'll continue covering this next time. Have a nice day.